Hello everybody, I'm back. Again, my name is Masood Olia and I'm a professor here at Bedford University in the School of Engineering and in Mechanical Engineering Department. As I promised you, I'm back with more videos after pandemic. And here I have a problem which may be similar to the problem that I showed you with the concept of work energy and specifically with efficiency, power and efficiency. But this one actually is a different problem for which I want to use actually the principle of impulse and momentum. So that's what I want to do. Even though you could actually solve this problem by second law, but since right now we are covering the impulse and momentum in the course, currently I'm teaching dynamics, might as well just use this approach. Okay, so the problem states that we have a mass, a load of 100 kilograms, a crate of 100 kilograms being lifted by this hoisting mechanism, where the force coming from the motor here is given to be a variable force. You'll see that anytime you have a variable force, and your variable force is actually a function of time, it is the method you want to use, a convenient method would be impulse and momentum. So when force is a function of time, that's what you want to do. Okay, so anyways, so this is initially at rest, so V is 0 initial velocity, and then once we turn the motor on, the force given by the motor in this cable attached to the motor is 10 t squared plus 300. Force is in Newton and time is in seconds. We want to find velocity at t equal 4 seconds. What you have to be careful, guys, with this type of problems is that we don't know if the motion is going to happen right away. In other words, when the motor is turned on and the tension is given, is it going to move right away? So you always have to check to see when the motion starts. If the motion starts at t equals 0, fine. But in this case, actually, that's not the case. So if you draw a free body diagram, notice that the weight of this guy is going to be 100 times 9.81 or 981 newtons, right? And notice that the tension here with this hoisting mechanism that we have, effective tension is going to be 3 times that force that is coming from the motor. So in order for the motion to happen, at least you have 3F equal to what? 981. Right? Or F equal 981 over 3. And what is F? F is 10 t squared plus 300 equal 981 divided by 3. So if you solve now, I'll move down here. 10 t squared equal 981 over 3 minus 300. Whatever this comes out, divided by 10 and take the square root. Guess what? T becomes, I have written it down here, T is actually 1.6432 seconds. So the motion doesn't happen right away. It will take a little bit more than 1.5 seconds for the motion to start. So now what does that mean? Our T1 is 1.6432 and our T2 is what? Is equal to the time at which we want to calculate the speed. These are in second, of course. So this is what we have to be careful. The impulse then has to be calculated over this time period, not from 0 to 4 seconds. So what is the principle of impulse and momentum? Change in linear momentum, mv2 minus mv1 is equal to impulse. Impulse in general is the integral of sum of the forces. Remember, this is a vector solution, guys. Okay, not to be mixed up with what? Work energy, which is a scalar. So you could write this equation in any direction you want. Of course, our motion is in the y direction. So if we take this to be a positive direction, I can rewrite this again as mv2 minus mv1. I'll just call this impulse. Now, impulse, remember, is just the integral of force with respect to time in general over the time where the motion is taking place. So in this case, look, our initial velocity is 0. our mass is what? This is what our mass is 100 kilograms. This is metric system, right? This V2 is velocity at t equal 4 seconds. Equal impulse. What forces do we have? Direction is important, guys. Look, we have impulse of 3F and we have the impulse of the weight. 3F is in the positive direction because the force is a variable. That means that we have to integrate 3F with respect to time. And the key is that now you're integrating from when the motion starts to when you're trying to calculate the speed. And then minus the impulse of the weight. The weight is a constant. If you have a constant, the impulse of a constant force, you see if you had a constant here, right? It would be what? It would be just the force times delta t. So in this case, the weight is 981, and delta t is what? Delta t, I'll put it down here, guys, for you. Delta t is the difference between T2 and T1. So again, typical mistake is that you just use 2. So that would be what? 2.3568 seconds. So go ahead, plug in. I'm not going to go through the integration. You know how to handle that. Can even take the 3 out. Integrate 10t squared plus 300. You could even put the tension within this integral, actually. I'm sorry, the weight within this integral. Okay, your limits are exactly what they were before, right? And then this one becomes 981 times delta t, which actually is this guy, right? 2.3568. I don't want to leave the frame here. Okay. Anyways, go ahead and solve for velocity. Remember, this is velocity at t equal 4 seconds. And I think the answer comes out to be 4.05 seconds. So this is the velocity at that particular time. You may want to check the math here by integrating and evaluating. All right, so another simple, really example, guys, of how we can apply the principle of impulse and momentum. Remember, this problem could be solved by F equal ma, second law. But again, the trick is you have to figure out if the motion is going to start right away. In this case, it didn't. So all the impulse is going to be calculated from the initial time to the final time. As always, guys, thank you for watching and listening. And I would really appreciate if you subscribe, and I will have more videos for you in coming weeks. Thank you.